Hey everyone, and in this video I'm jumping into what is AI. It's going to be a very basic breakdown of what AI is. It's going to use a lot of things called heuristics, which is a simple way to understand things that might actually be starting to be a little bit inaccurate because we're trying to simplify it so much. Because I really just want to give a 40,000 foot view of what AI is. And where I'm heading with this is how can we use AI to beat bacteria? Essentially, how can we use AI in drug design? So let me jump into what is AI. Now, statistics first. I'm sorry, guys. AI is kind of like a fancy form of statistics, so I need to explain statistics briefly in order before I can start jumping into what AI is. So statistics first. Here we have an explanatory variable, and here we have a dependent variable, and then we have dots in the graph, and there are different colors that might suggest that they're from different groups. Now, actually, it's typically a little bit easier if we start to actually put some example data in there. So our explanatory variable here is height, and our dependent variable here is weight. We're trying to predict how heavy someone is given how tall they are in proper units called centimeters and kilograms. Okay, here we go. So we want to answer, now all stats is about making predictions, right? We call them inferential stats because it helps us infer what's going on in the data, but really that data is only robust and those inferences are only important if they help predict the future, predict future samples, future data, future experiments. So we run a clinical trial on a drug to know that it will and predict that it will work once we take it out to a whole population. So if we find someone who's 180 centimeters tall, what would we predict their weight to be? So to do that first, what we would do is we'd draw a line. This is called a linear regression, and that line should closely model the data. What we will then do is draw a dotted line up from 180 centimeters and draw a line across to see how heavy we would predict that they would be. And the answer would be 79.5 kilograms. Well done. So that's our prediction using our statistical model. But somebody might ask, wait, how did you come up with that line? You just seem to draw a line that fit good. How did you come up with that? That's Francis Galton. He actually came up with how to do this. He's the statistician behind it all. Okay, so not a great dude though. Anyway, okay, so how did we come up with that line? Where do we draw that line? And that's where stats comes into it. Okay, there's a few steps. How do we know where to draw a line? Step one is measure the distance between all our data and the predicted value of the data. So we're making a prediction about the value of the data. So we would actually predict that this green square should be here. It should be on the line. The line is the prediction. We would predict that that green square is here. But we were wrong by this much. So that difference there is the line there, the distance between each point and the model and the prediction. So we take those lines. We take these distances, the first thing we do is square them. So we actually take that number and we multiply it by that number again, so we square that distance. Then we add them together. So we add all those lines together after we've squared them. And this is a statistical term called the sum of squares. It's quite nice. Sum means to add up. Squares is because we take that distance and we square it. And we draw a line that makes this sum of squares the least. How can we make once we add up all the distances between those lines, we square them, once we add all that up, how do we make that number, the sum of squares, as little as possible? And what you can see, hopefully, is if I were to draw my line there, I would have really big lines. I would have huge distances between the values and the predicted values. That's because it's not a good model. So we would have a very large sum of squares, and we haven't drawn the line that would minimize the sum of squares. We haven't drawn it in a place in which those lines would be the shortest. So if we move it back up to here, that is where we want to do it. It's the least sums of squares methods. Now, actually, all of these methods, linear regressions, t-tests, ANOVAs, even a mean, is a group of methods that we call the least squared methods, or the ordinary least squared methods. And that's because it aims to minimize the square difference. Why do we square it? Well, the answer is to punish being a long way away from it. So this one is going to have a great effect on the model than this one, because if you square it, that number becomes even bigger. 1 squared is 1. 2 squared is 4. So you can see the distance between 2 and 1 gets much bigger if you square it, right? So it's a way of emphasizing and punishing points that are really far away from the model. Okay, so how do we do that? How do we create a line that minimizes the sums of squares? I've really just kicked the can down the road. How do we find a line that minimizes the sums of squares? Well, it turns out there is a particular formula to it, right? You take all the values of x, you multiply it by all the values of y, you add that together, then you subtract all the values of x, added together times all the values of y added together, so on and so forth. It's a complicated statistical formula. It was done by Francis Galton. But the important thing is not really what the formula is or how it works. The important thing is that in statistics, we have a bunch of formulas that calculate the line that generates the least sums of squares, right? So that's the important way to do it. And so everyone, everywhere, using this formula could create a line that minimizes the sum of squares and minimizes the distance between the data points and the model squared. All right, so how would AI do it? I just mentioned that AI is really just fancy statistics. What approach would AI take to this exact same problem? Well, it follows some different steps, okay? And you might be like, these are some peculiar steps, but yeah, this is how AI does it. First of all, draw a random line. This is what AI does. You draw a random line. So we're drawing this line, not a great line, but that's the line we're drawing. Next, you take the sums of squares. Now, this isn't what always happens in AI, but this is how AI would approach this problem. So we're going to work out the distance between all the data points. Then we're going to square them, then we're going to add them together. That's a certain formula as well, by the way. That's a formula. Take the point minus, take the distance between the point and the model, square it, add them all together. That's a formula to create the sums of squares, right? Now, what we would call that formula is we would call it a cost function in AI. It is a formula that generates a number, and that number tells you how bad your model is, right? So we call that formula a cost function, and the sums of squares here really is just a score for how bad your model is. So using the cost function, what it does then, AI, is it takes that formula that we used to generate the cost function, and it figures out which is the best way to go. Should I rotate that way or should I rotate that way? What's the best way to go next, right? And then once it figures out that, so it uses the formula that calculates the cost function, which is the formula that calculates the score on how bad our model is, which is sums of squares. It actually manipulates that formula to figure out, it differentiates it, but anyway, to figure out what's the best way to go. And then once it figures out what's the best way to go, it's going to move that way slightly, because it doesn't actually know how far to move. All it knows is to move that way. So then it's going to move that way slightly. So here we can see it's moved slightly, and it's improved the residual sums of squares, or the sums of squares. So the number that tells you how bad your model is has gone down, right? We've decreased the sums of squares, and the sums of squares is the number that tells you how bad your model is, because it tells you how far away your data is from your model. We're still a long way off though. So what does AI do? It repeats it. It repeats those exact same steps. It adds up the sums of squares, that scores how bad your model is. It then uses the formula to add up your sums of squares to predict what's the way to continue to go, and then it moves that way ever so slightly. And so it's going to repeat that, and it's going to repeat that, and it's going to repeat that. And in AI modeling, we call this training. We are training the model to the data. So it's going to get better and better and better. Now, eventually, it's going to get to a place where there is no way to improve the model. The line's going to go, okay, hang on, let me calculate which way should I go. There's no way to go to improve the model. I've actually improved the model as much as I can using the tools that I've got, so that's as good as I can get. This is how AI would build a linear regression. Now, if we were to plot that cost function I kept talking about and that sums of squares model, it would look like this. So iteration is just attempts, it's repeats. How many times have you repeated? So the first time you run the AI model, it's terrible, it sucks, it hasn't been trained, right? So this is the output of the cost function, i.e. it's a score of how bad your AI model is. And in the example that we're doing right now, it's the sums of squares, because that tells you how far your data is away from your model. So we've got a very large sums of squares because the first time we ever run our model, it's bad, right? Because it's random. So then we figure out which way to go and we move our model ever so slightly and it improves our model. So then we keep going and going and going and going and we repeat. And every time we repeat, so far, we've improved the how bad our model is score, right? So we've run the cost function, we've run the calculation, how bad is our model, and every time our model gets slightly better as we continue to improve it. And as we go through the iterations, we're eventually going to get to a point where any attempt to improve the model will just make it worse. So in fact, we won't even do that step. It reaches the point where it looks in every direction and it goes, there is no way up from here. There's no way down from here. I've reduced my cost function as much as possible. I've reduced my sums of squares as much as possible. This is as good as I can get, right? Now, the funny thing is the output from the AI model will be exactly the same as the output for the linear regression, right? Which was a simple formula that took 1 second to calculate. You could do that by hand, but instead we had to run the model over and over and over and over again using complicated statistics, and we had to do differentiations and all sorts of stuff, and we ended up with the exact same thing. So you might be sitting to yourself going, why? Why would AI do it this way? What the heck are you doing, AI? Are you drunk? This doesn't seem like the right way to go. Let me explain why it is the right way to go in some situations. Okay, so first, complexity. Let's imagine instead of our data looking like this, it actually looks like this, right? So first of all, we have a lot of data and perhaps it's more complicated than we expect. Maybe there's some stuff going on the inside there. It's a little bit more complicated. So if we were to run our linear regression, we'd just whack our line right through there. Job's done. You can see that I'm not very close to my points, right? I haven't really been able to predict anything that's going on up here or anything that's going on down here. I haven't made some good predictions, right? So what AI might first recognize is, hang on, actually, there's 3 groups in here, not 1. And second of all, it might draw some very complicated models that aren't linear. They're not any simple mathematical model. They're not polynomial. Who knows what the heck they are? They're just completely crazy. And they might draw these crazy models that really tightly predict the data. And so if there is a heck ton of data and the data is incredibly complex, then perhaps AI is a bit better than a linear model because it can start to figure out these relationships that any sort of intuitive statistical model couldn't figure out. So complexity is one reason to use AI over linear modeling. But we can do linear modeling in some fairly complex data. So are there any other reasons? Well, relationships beyond human understanding. So if your data is rich enough and big enough and large enough, say like what Facebook's got on every human being on the planet, basically, they have a very rich data set with so many data inputs going on there. And they have a huge number. They've got billions of people in their database, right? So they have a very rich data set. This is again where AI can start to get really, really handy over linear models. And we can start to see relationships beyond human understanding. So see these 3 groups. It's no exaggeration. Maybe it's a little bit of an exaggeration, but not too much of an exaggeration. Perhaps AI found these groups to be, if you are from New York and like the show Walking Dead, then you have a specific niche relationship between height and weight. Something a human couldn't understand, but AI has figured out actually there is something to this. That there is this niche of people that are from New York who like the Walking Dead that have a unique relationship between height and weight. Or maybe you eat in the car while singing along to Tay Tay, right? And that might be the blue line. And the green line is you might eat Weet-Bix 2 out of 3 meals. You're from New Zealand, you live in Tasmania, you're bald, and you sing along to Tay Tay. So maybe that's me. Maybe there's me and people like me. That's my model there, right? So AI is able to build up these relationships that no human being would ever believe makes sense to do as a relationship. And we can actually see this with a little bit of a side note. One of the first things we used AI for was playing chess and Go to sort of demonstrate the potential. These are board games to demonstrate the potential of it. And humans have said that they can, grandmasters, really good players, can recognize that they're playing AI because they're doing things different, right? So they've figured out how to play a game as old as time differently to how the humans are doing it. They've built these relationships that we couldn't see and don't seem to make any sense. Whenever you see someone, if you watch a YouTuber called Levy break down chess, who'll be like, the AI suggests to do that, but I have no idea why. And so like really good chess players can't figure out why the AI is making the moves that it is making because it's built up these relationships that humans can't understand. All right. The other thing is inputs into AI are normally extremely complex. And what do I mean by that? Well, here we have, this is a two-dimensional plane, right? We've got one plane here, and we're trying to put a line across. Now you can imagine adding another variable into the page, into the Z direction here, and turning it into a cube. So here we've got a cube here, and what we might have, a real simple one might be height, waist size, and weight. And you can probably guess we'd get better at predicting your weight if we knew your height and your waist size. That would be two very important bits of information in predicting your weight. Well, AI can handle really well, not 2 dimensions, not 3 dimensions, but thousands of dimensions in the data. And it's kind of hard to understand, but it can build these complicated multi-dimensional planes that track the data. So if you imagine you need a line to explain 2 variables, but you need a surface to explain 3 variables. That's what we can see there. But imagine thousands of variables. What do you need this multi-dimensional surface that can pick out and model all the data through all these complex interactions. So it allows for interaction effects between these 2 variables. Again, maybe you're in the car and listening to Tay-Tay interacts in such a way to influence your output in a really unexpected way in this multi-dimensional landscape that AI is navigating. Now, linear models can do it too, but they're much cruder and much more difficult. Like, for example, on a 2D plane, largely they would try put a flat sheet unless you try to tweak the complexity and turn it into a simple curve. But now you're starting to again try to get that human brain to try and guess the shape of the relationships in that 3D plane. Now imagine it's a 1,000-degree plane. What possible shape could a human imagine in terms of the mathematics trying to put that together? AI can do that. Why? Because it just chucks in a random sheet and then it tries to improve it, and then it tries to improve it, and then you do it thousands upon millions of times as it slowly changes its shape until it finds a perfect shape that it can't improve on after that. Now, one of the problems here is overfitting. Now, what would happen if you got new data? You might find that new data, so you train the model on this data, and you got these outputs from the AI. And then you go, great, now I've got an AI model that fits my data perfectly. I'm able to make these perfect predictions from my model. It's amazing. And then you go collect a little bit more data and you see that you end up with some orange triangles there that are sort of way off the line. You end up with some blue circles there that are way off the line, and some green circles there that are way off the line. And now you can see maybe there's a 4th group in here. Maybe this would have been better modeled by a straight line. Same with this one. And this is called overfitting. It's when you've perfectly designed yourself with the data you've been exposed to, but then you chuck in new data and it doesn't work at all. And it's because you overfit your model to perfectly shape your existing data, but the model made no actual logical sense. Perhaps it makes no logical sense that someone who eats whilst driving listening to Tay-Tay has this line here. Maybe that is completely illogical, and so it's not robust. We call this a lack of robustness. So any new data, it doesn't really work. So to get around this, what we do with AI is we sometimes train it many times on different data sets, but we often also split our data set into a training data set and a test data set. Now, often 80-20 is a standard way to do this. So say you're doing it on the Facebook data set, it's got 1 billion people. You might save 200 million of those people and not expose your model to it. And then you train your model on 800 million people, and then you test it against the 200 million people to make sure that your model is robust once you start looking at new data. Then you can start to do fancy things like you put that 20% back in, you retrain it on a new 80% that included that 20%, and you leave out a different 20% of the data set, and you can do that multiple times and so on and so forth. But anyway, the point is you test the robustness of your model by training it on a fraction of your data and then testing it on the leftover fraction of your data, just to make sure that your AI is robust. But you might be wondering, wait, how do you get from these lines to this, which is I've asked ChatGPT to write a Taylor Swift song about immunology. And it's written a whole 5-verse song with a bridge and an outro, a 2-verse song, 3 choruses, a bridge and an outro. Pretty good. I'm going to say I'm not impressed with the chorus. The chorus is, oh, my immune system's a superhero fighting all the bad guys. It's always on the go. White blood cells, antibodies protecting me from all the diseases. I'm like, where's the rhyming, Tay-Tay? But there's some good Tay-Tay stuff down here. Vaccines, flu shots, building immunity, memory cells remembering the enemy, T cells, B cells working in harmony, killer cells attacking the enemy. Okay, she rhymed enemy with enemy, but it is just an AI approximation of Taylor Swift. So let's not hold it against Taylor Swift, okay? So how do we get from these random linear models to this? And you're right, there's a heck ton more going on. A lot of it's about, I can't even go into it, right? I work in an office with an AI guy, and he tries to explain some of these complex stuff to me. But it's about condensing the words down into data, into specific bytes, and it might be one word, or it might be several words. And anyway, okay. So how do we get from lines to this? Broadly speaking, these are language models. What they do is they take the words that you've inputted and try and predict the next word. So what you might see something like this is what word follows Taylor, and it would have a probability map, a probability landscape based on the words before Taylor as well. So you've got all these words building up in this multi-dimensional landscape, and then I think ChatGPT has about 12,000 axes on its graph. It's 12,000 dimensional approximately. So you can imagine, based on the certain combinations of those words leading up to the word Taylor, what is the next word? And it will have a graph like this, and it will predict the highest probability of Swift. After Taylor is Swift, maybe it's Taylor Tay-Tay, maybe it's Taylor Lautner, maybe it's Taylor Made. That's a golf brand if you haven't heard of it. Taylor Glitch is apparently an anecdote, maybe misspellings of Swift, but it will look something like this, and so it will predict that the next word must be Swift. And then it will go back into its model and say, okay, what's the next word, and what's the next word, and what's the next word? So you can see that it is still really just, instead of predicting height, which is a numerical number, it's just predicting the probability based on all the words in its database. What's the next potential word? So hopefully that kind of makes sense in AI. Right, so that is AI, and you can see that it's perfect for this problem of drug design. Here we have a complicated model. This is a complicated chemical. How do we know if this chemical is going to be a good antibiotic or not? There's no linear regression that we could use that would turn this incredibly complicated molecule and give us an output that tells us how likely it is to work against bacteria as an antibiotic. I mean, they kind of are, but it's very, very difficult. AI is going to be much better at this. This is perfect for it. We've got a complicated drug design, and we have a rather simple cost statistic, which is how effective is each chemical at inhibiting or killing the bacteria, right? So it's very easy to get your numerical output on this. How good is it? You know whether this was a good drug or not. So we're going to have some really good data, and we can build it. It'll probably be a sums of squares model again, something like that, to build a model that fits the data as best as possible. The hard part would be is you can, but not really. It's very difficult to show AI a molecular structure and ask it, it might be a lot easier to turn that into a numerical value. Now that's going to be hard, turning into maybe several numerical values, a long chain of numerical values. So now you've got a good data set to pop into your AI. So I'm going to jump into that in a video much later on, where I really jump into this paper that actually used this and actually discovered new potential antibiotics using AI.